Welcome to From the Near to the Far, and in this session, I'm going to discuss a few alternative trajectories to quantum computation. At the outset, I'll say that quantum computing is considered to be an area with massive potential, and this derives from two considerations. First, from the promise of exponentially speeding up computing by leveraging quantum mechanical properties, and as we know, this is the focus of the quantum computing industry today. The second consideration that I would consider to be more germane is the fact that the quantum realm separates the visible from the invisible. And that implies that no matter how much we know, there will always be more that we do not know. And this in turn will always be a source for new technologies that will continue to drive us far into the future. So in this session, I want to provide an approach to penetrate the unknown by using the double-slit experiment and surfacing technologies that will then contribute to alternative trajectories of quantum computational development. The structure of this session is the following. We're going to first examine the double-slit experiment. This will lead to a discussion of the quantum computational whole. We'll further add insight from different observers within the double-slit world, and this will yield to consideration of different quantum computational approaches. And I'll end with a brief summary of key points in the session. So let's look at the double-slit experiment. Here I use an extract created by PBS Digital Studios. It's called the Quantum Experiment That Broke Reality. And as a reminder, the double-slit experiment is where we send light through a double slit, and there's an interference pattern that results on a screen behind it. What the key point about this experiment is that even when we send individual photons one at a time through the double slit, it still counterintuitively results in an interference pattern.
And each bundle can't be broken into smaller parts. That means that each photon should have to decide whether it's going to go through one slit or the other. It can't split in half and then recombine on the other side. That shouldn't be a problem, as long as you have at least two photons. One photon passes through each slit, and then the two photons interact with each other on the other side and produce our interference pattern. But here, we get to one of the craziest experimental results in all of physics. The interference pattern is seen even if you fire those photons one at a time. Well, let me back up a bit. The first photon is detected as having arrived at a very particular location on the screen. The second, third, and fourth photons also, they deliver their energy at a single spot. And so they appear to be acting like particles of well-determined position. But check it out. If you keep firing those single photons, you start to see our interference pattern emerge once again. By the way, Veritasium actually conducts this experiment in his excellent series on the double-slit experiment. Really worth a look. This is so bizarre. This pattern has nothing to do with how each photon's energy gets spread out, as was the case with the warp wave. Each photon dumps all of its energy at a single point. No, the pattern emerges in the distribution of final positions of many completely unrelated photons. How can that be? Each photon has no idea where previous photons landed or where future photons will land. Yet each photon reaches the screen knowing which regions are the most likely landing spots and which are the least likely. It knows the interference pattern of a pure wave that passed through both slits equally, and it chooses its landing point based on that. It turns out that the photon isn't the only thing that does this.
So let's reflect on this experiment. I'm going to summarize some key thoughts. First, the key point is that photons projected one at a time through two slits create wave-like interference patterns on a screen behind. And as suggested before, this is counterintuitive, and it also indicates that embedded in a photon, there is both a dual particle and wave-like behavior somehow. So it's almost as though each photon has a knowledge of the interference pattern and knows where to fall on the screen to adhere to that. So in a sense, in a way that we can look at it, an individual photon appears to be crossing limits of time to share knowledge with past and future photons. In doing so, it's displaying superposition in that it adheres to wave knowledge of many possibilities until it hits the screen. And also there's an implicit phenomenon of entanglement because all the photons are connected to one another in this experiment. So let's step back and look at a couple of interpretations. There's the common interpretation that I call a bottom-up or reductionist interpretation, and that's the key points I just went over a minute ago. But to summarize, if we take this, it's from the point of view of each photon, and then the perception is that the photons connect to past and future and assume infinite values before they hit the screen. Now, if we consider a different interpretation, a top-down interpretation, and in that interpretation, the same experiment is viewed as a totality so that no part can be separated from the whole, then what arises is a suggestion of a minimum viable whole that somehow is wrapped in the space-time configuration encompassing the experiment. So here is an illustration of the experiment. And looking at it from the top down, this quantum computational whole, we can refer to it as fx, where x can be considered some kind of light and f is a function. So it's displaying some behavior of light, some kind of quantum mechanical, quantum dynamical behavior of light. And in particular, in this interpretation, each photon can be thought of as being linked to a property of x, and these properties can be a set from x1 through xn. And so as a photon travels and then hits a screen, it's correlated to a function of the property, and that's how it shows up in a particular strand that is expressing that function of a property that belongs to this wholeness that is attributed or is referred to as fx. So here, really what this boils down to is that there's a functional aspect that comes to the forefront, and each individual photon contributes to the final interference pattern based on a functional basis. So it's a completely different interpretation from the bottom up. And again, it doesn't require that photons have knowledge of each other because they're each endowed with a specific function right at the outset. And it doesn't require that there's a connection between past and future photons either. So before we continue, just take a quick pause and consider where it is that you land when you think about this experiment. Is it more of the reductionist approach or the bottom-up approach, or is it the top-down or the viable whole, minimum viable whole approach? Now, when we consider both these approaches, I want to introduce us to a cast of actors in this double-slit play, if you will. And we've already been introduced to fx, which represents some kind of whole. And here the whole is the behavior of light across the double-slit experiment. When we consider or look at this behavior from the bottom up, that is, we somehow decompose fx and we measure quantum objects that occurred during this experiment, then we arrive at an actor called qfx. So it's some kind of function of this larger fx. And this will yield another set of actors that we can refer to as q properties. Now, when we look at the same experiment from the top down, then as I suggested, there's x properties x1 through xn that are created. And then there's another actor, a function of these properties referred to as fx. And subsequently, I'm going to introduce another set of actors, gx and rx, that can be thought of as more developed forms of fx. And also, this is going to lead to another set of actors that also will be introduced soon, what I'd refer to as a minimum viable whole. So some kind of purer form of fx looked at from the top down, as opposed to qfx, which is looked up from the bottom up, and then a more sophisticated form of ufx that we can refer to as vfx. And finally, there's another couple of actors to be introduced to. There's another whole, just as fx is a whole. And here, the idea is that as these wholes interact, they create a new possibility that's represented by this combined whole function. The point of this is that as we consider these different actors that arise in the double-slit play or world, then there's different quantum computational approaches that are suggested by it. So there's an approach that is based on this bottom-up rendering of this wholeness here. There's a rendering in terms of top-down leveraging X properties. There's a more holistic rendering of the top-down in terms of the UFX, VFX. And then there's also a trajectory of development based on interaction of wholes. So I'm seeding some different sets of factors here and potential dynamics that occur when we consider them, and we're going to go into this in more detail. The question, before we go into more detail, is what is the current computational approach, quantum computational approach, with regard to this set of actors? Now, as I suggested, what we appear to be doing right now is going through a process of decomposition and recomposition, in that we're measuring some aspect of the whole, and that results in something that we're calling QFX. And then we're subjecting that to probability and statistics to arrive at a probability-based wave-like function. So remember, in the double-slit experiment, we're looking at an interference pattern, but we're reconstructing or recomposing this interference pattern by measuring reduced quantum objects, subjecting them to probability and statistics to come up with a probability-based wave-like function. And I want to suggest that this probability-based wave-like function is different than the original double-slit interference pattern. And so what we're in fact dealing with, or in our default quantum computational approach, we're actually doing something different than the possibility that's being suggested by the double-slit experiment. And we're going to go into this in more detail. So the question is, when we consider manufactured qubits, what exactly are they adhering to? Because depending on what they're trying to represent or how they're operating, it's actually different trajectories of quantum computation that potentially are being leveraged. And here, I want to suggest that it's primarily the QFX Q property that all manufactured qubits adhere to. And so there's an opportunity, or there's a gap in that the manufactured qubits don't necessarily adhere to or follow the possibilities laid out by FX, UFX, and so on. I also want to draw attention to an analogy, and this is by considering the realm of space and time. We know that there's a limit to how accurately we can perceive or measure space and time. And as some hypothesized, it would require an infinite amount of energy to penetrate into the smallest quantums of space or time. And this would result in a paradox, because the local space-time would then collapse into a black hole, breaking down all laws of physics, meaning that it's impossible from this point of view to actually penetrate into the quantum of space and time. We have to consider that level of wholeness when actually we're dealing with space and time. So there's a granularity. And I want to suggest that perhaps there's a lesson to be learned, or there's something that also applies to the standard quantum computation approach, because we know for a fact that we run into phenomena such as decoherence, lack of stability, lack of ability to propagate quantum states, and so on. And the question is that because we're running into a fundamental limit where we in fact need to step back and measure, quote unquote, measure things differently? Or is it due to a lack of maturity in basically our understanding of the quantum realm and our ability to create qubits that are able to deal or interact with that layer of the quantum realm? So this is something to consider as we go forward. So summarizing the key points of this section, there's a quantum computational whole that's represented by Fx when we look at the double-slit experiment. In my assessment, we are in our current quantum computational approach, we are decomposing and recomposing Fx. So the focus now is not on Fx or the possibilities that Fx renders, but on possibilities that QFX renders. And so the point being is that there are other paths beyond QFX that should also be possible in terms of trajectories for quantum computational development. So let's dive into this idea of the quantum computational whole. And the way I'm going to do that is to construct a world based on the double-slit experiment. And we're going to consider each photon that originates in the quantum computational whole, this Fx, as bringing forth or carrying something of Fx, as I mentioned earlier. So Fx can be thought of as having unique and distinct quantum properties represented by the set x1 through xn. And we see an indication of that set spread out over here and contributing or being instrumental in creating this interference pattern. Each photon can then be thought of as being related to or derived from one of the elements in the set. So each of the photons is related to x1 through xn, and it takes on the form Fx as rendered over here on the screen of the double-slit experiment. So in this thought experiment, each of the strands highlights a unique aspect of Fx, and each of the strand comprises of similar photons, but yet each photon is different in that there's a subtle variation or nuance that shows up in the fact that it takes on a different position within the strand. So let's imagine that this layer is the base layer in this double-slit world. And the point being is that it manifests something of Fx. So it's bringing forward, or it's showing us the whole that's contained in Fx through these different strands that are related to Fx1 through Fxn, but it is not able to bring out more of the whole, it's bringing out some of the whole of Fx. So the question is, how in this thought experiment can we bring out more of what is in Fx? So if it's a whole, then how do we approach the limit of what that whole is? And so we can do this by creating a second layer that's built on the first layer. And the way that we would create it is that each of these functions can be thought of as sets, as I suggested earlier, containing practically infinite number of unique photons. And so we can take elements from across these sets and combine them in unique and distinct combinations. And that would be the basis of creating a second layer, which we can call GX, which in fact is bringing forward something else that exists in the whole. So mathematically, it's expressed in this way. And the point being is that GX is now showing us something more beyond what fx was showing us of what is contained within this whole over here fx. And we can then continue this process with surfacing different layers and combining them in different ways. And I'm going to refer to that evolving form that begins to approach the wholeness of fx as rx. So now we've been introduced to the idea of the x properties of fx that derives from that or is determined by that, by a gx that's built from fx, and then an rx that is built on gx, and then rx is an evolving form. And so this line of development over here is pointing to another quantum computational approach and trajectory that's possible. So if we want to create this different quantum computational architecture, the first thing is that we have to realize or imagine that this whole, that we're not dealing it because we're dealing with something called QFX, also exists. And then we need to have instrumentation that's based on fx, gx, or rx, where again, r is some evolving functional form, in an endless journey that continues to express more of what fx is. And so, in other words, this instrumentation, the logic, the mathematics, the gate structure of this quantum computational architecture has to be based on rx. So now let's add some insight from different observers in the double-slit world, and that'll help us transition to looking at different architectures that contribute to different parts in a roadmap. So observer one, I'm going to say, is our current quantum computational approach. And as I suggested earlier, this is due to decomposition and recomposition of fx, employing probability and statistics. So the observer is actually the act of employing probability and statistics. And this results in QFX that I'm proposing has nothing of the wholeness of fx. It's something different that we're actually dealing with. And fx still exists as a whole, but we're not dealing with that anymore. We're dealing with QFX. And if fx contained properties, x properties, then we can think of QFX as a different set of observed properties, Q1 through QM. So we're now dealing with a different set of properties that still can be combined together, can be leveraged for superposition and entanglement. And in a sense, what we appear to be doing is building a different layer for computation, leveraging quantum computational properties. But again, it's not related to this aspect of fx that would require a different kind of architecture. So any Q element of this set, as I said, can be superposed. Q elements can be entangled. And the quantum computing possibilities of QFX will be based on the Q set. And again, will have nothing to do with fx. So Q set is can be considered to be this over here. So let's think about this Q set in a little more detail. So in today's rendering of quantum computation, qubits can be based on a variety of quantum objects, ions, electrons, photons, and so on. And as I said, they display quantum mechanical properties such as superposition and entanglement. If we to think about what players today in the quantum computing industry are doing, then some players are following this approach where they group together a threshold number of qubits, learn to map a real-world problem to them, learn to leverage superposition and entanglement to process the possibilities, and in the process, address a variety of traditionally intractable computational problems through this approach. In the second approach, the qubits can be made to represent atoms and molecules. or even atoms and molecules can be harnessed to operate as qubits within a controllable gate-based quantum computational architecture. And then there's a different way of applying quantum mechanics and speeding up the computational process. So in themselves, these are, of course, great possibilities, and they need to be further developed. And that's what's going on today. However, paradoxically, I want to emphasize the point again, is that the mechanics of the manufactured quantum objects haven't captured that quantum hole that keeps silver operating as silver, or the integrity of a particular protein intact. But we're dealing with, in fact, creating another layer of computation that allows phenomena such as superposition and entanglement to potentially be leveraged. Now let's consider a second observer. And here, the observer can be thought of as placement of a measurement device between the double slit and the screen behind. Now, depending on how this measurement takes place, it could result in a Q property or an X property. And if it results in a Q property, of course, we're going down the observer one scenario that we already discussed. If, however, it is able to measure the X property, then potentially we're going to go towards more of the wholeness of what Fx represents and go towards the concept of a minimum viable holes represented by UFX and VFX. So that's a second possibility. Now, let's consider a third observer. And the third observer can be thought of as represented by the screen. And we know by default that the screen is displaying X properties of Fx in the form of the Fx actor. And so there's a different kind of wholeness that's already represented there. And so what this possibility represents is building on function and moving towards UFX and VFX in a more secure way. And then finally, we have the fourth possibility, computational possibility, which is the intersection of holes. And this would require a fourth type of observer. And another hole, and this, let's think about this. This could be an observer watching the double-slit experiment that has a certain emotional or thought bias. And in this setup over here, that bias would then influence the behavior of the experiment in some way. And there's been some indication and experimentation that objective reality can, in fact, be influenced by intent that different observers have. So this intersection of holes represents a fourth quantum computational paradigm or trajectory. So to summarize, the point of view elaborated here is that the quantum level is complex, sensitive, adjustable via feedback. And there are different ways to conduct quantum computation that will require different architectures and result in completely different outcomes. So when we think about scenario one, I'm proposing that's the default industry approach. And when we think about scenarios 2, 3, 4, these represent unique and new different quantum computational opportunities where we're dealing with the evolving form Rx to get to more of the wholeness represented by Fx. And to my knowledge, we don't have quantum computers that are actually doing that right now. So looking at some technologies, when we consider the observer one scenario, I'm suggesting this is the commonly accepted quantum computing species, in which quantum objects are subject to statistics and probability. And then these quantum objects allow entanglement and superposition and computational speed up. And we can see representations of existing technologies that are based on this. When we consider scenario 2, then we actually are looking at a different kind of technology, what I'd call a function-based quantum computer. And as a reminder, this is when you place a measuring device close to a double slit. Then, depending on how the measurement takes place, you could be allowing more of the computational whole to be, the quantum computational whole to be measured. And that, however, would require a different measurement paradigm and would require gate structure that would propagate function and property of that quantum computational whole. So if we think about silver as containing different functions, for example, like malleability, ductility, conductivity, resistance to oxidation, and so on, then what's being proposed here is that we have a function-based computer where the gates are actually pushing forward some function, so malleability. And the possibilities of this are essentially taking the whole of what silver represents and then computing with that to combine them, say, with what gold represents, and bringing something different forward. So that's the function-based quantum computer. And the mathematics would not be based on probability and statistics, but would have to be based on function. So there's a function-based mathematics that would be required. And the gate structure and logic would also be built on this. Now, coming to a third paradigm, when we look at the quantum computational wholeness, so we can think of observer 3 as representing more of the wholeness, using the strands as a metaphor. And so the computer at the outset looks at the quantum level differently. And again, there's different combinations of gates, and there's a higher level of computing sophistication than in the previous scenario. And there's therefore, we'd be able to arbitrate at a higher level of wholeness, and there would be a larger range of functions that then becomes possible. I've done some baseline thinking on this and have published a number of IEEE articles that look at anchor points in today's quantum computational approaches that were suggested by Feynman's work or Euler's or Schrodinger's or Heisenberg's, and I've extended them to, in a sense, think about these or consider these other computational paradigms. I'm happy to share these if you reach out to me. And then finally, we have the fourth technological paradigm of wholenesses interacting. And this is the observer 4 scenario, which would be based on a function-based quantum computer. And in this scenario, human beings would be part of the quantum computational architecture. And again, I've done some baseline thinking on this and published a couple of IEEE papers that, again, I'm happy to share. So summarizing, if we think about the double-slit experiment and the play in the world that it creates, then to get to that function-based thinking, let's translate the mathematical representation of these actors into the essence of what they perhaps could stand for. So here we have fx, that's a hidden empress. So the way that she operates and what she represents remains in the background. We've got qfx, that's a utilitarian administrator. So taking some aspects of this so that there's a speed up in computation possible. There's q properties that would expedite that through some kinds of commercial factors. Then we have the top-down set of factors. So there's x properties that perhaps represent some ideas and virtues as opposed to commercial factors. And you got fx, that's an idealist, so building based on bottom-up in a completely different way. You got gx, who's an architect, building on this layer and creating the foundation for further development. You got Rx, that's a warrior that continues to break through barriers to get to the wholeness of FX. And then you've got UFX, who's a magician because she's able to either disappear or appear, go back to QFX or develop more of FX, depending on the situation. And then you got VFX, who's an artistic scientist that builds on the art represented by the whole, but using the science represented by QFX Q properties. You've got another wholeness represented by FOXO, that's an emperor. And when the emperor and empress get together, there's a new kind of empire that's built, and that's represented by FOXO. So coming to the roadmap, we have existing quantum computational approach that I would say focus on QFX Q properties, and this, as we know, the trajectory of development is ongoing, and it's suggested that it will take another decade or so to get to the kind of quantum computers that we would need to easily solve real-world problems. And then we've got this whole second line of trajectory of a roadmap, which is the function-based quantum computers for measuring differently, and this would deal with FX and X properties. You've got more sophisticated function-based computers that deal with UFX, VFX, GX, RX, and you've got wholenesses interacting that deal with FOXO and so on. So key takeaways from this: the double-slit experiment can function as a simple framework to make an exploration into the quantum unknown, as I've suggested in this session. When we do this, there are unconsidered potential technologies that will surface from such an exploration. And here I've suggested some function-based quantum computers based on wholeness and a different mathematics and logic and gate architecture. And finally, there's a dual-track quantum computing roadmap that leads us from the near to the far. We're certainly well down one of these tracks, but there's a second track that also needs to be developed and represents a lot of possibility from the near to the far.